So for this lab, we actually wanted to measure coma and astigmatism aberrations. And we'll begin with coma, and the way this behaves is as the wavefront is traveling through the exit pupil, the rays actually focus at different locations, which causes different magnifications with respect to the pupil zone for our image, and it results in this coma-like pattern. For astigmatism, the sagittal and tangential rays focus at different positions. So we have our sagittal rays traveling, and they usually focus further than our tangential rays. So it follows tangential rays, the medial focus, and the sagittal rays.
So here we have our experiment setup. We have our incoming beam going through the Hartmann mask, the lens, the microscope, and finally our image plane. We set our microscope right on axis to align everything, but to be able to measure off-axis aberrations, we have to actually move the microscope off-axis. So that we move it perpendicular to the rail to be able to measure coma and astigmatism. You can see here both coma and astigmatism are dependent on H, or our field angle, so we won't actually have either one of those on axis, which is why we have to move the microscope off axis to be able to measure those aberrations. Alright, so here we have our breakdown for astigmatism and coma. Here we have our Hartmann mask. To measure tangential astigmatism, we block the right and left holes and allow the beam to pass through the other three holes. And to measure the sagittal astigmatism, we let it pass through these three holes and block the top and bottom hole. To measure coma, we're blocking all except one hole. So for tangential, we let it pass through either the right or the left hole to measure coma. And for sagittal coma, we let the beam pass through either the top or the bottom hole and block all the other ones.
In today's lab, we wanted to measure off-axis aberrations. To begin, we had to create this setup right here. We started off with the Henny laser, and we made sure that it was aligned to the optical axis of this rail using an aperture slot. We then inserted this mirror and did the same procedure to align the optical axis to this rail right here using an aperture. Then we put in this microscope with an objective of 0.25 NA, and we aligned the crosshairs to the laser. Next, we created this beam expander, 10 micron pinhole, and we sent the expanded beam through the mirror and onto this Hartmann mask that's in front of the lens. The Hartmann mask has 5 holes, and 4 of the holes are on the outer edge of the lens, and there's 1 hole in the center. So when projecting that, it basically projects 5 dots, and we positioned it so that it focused onto the focus of the microscope so that we could see the Fourier transform on the image screen. Now, I don't know if you can resolve this on the camera, but if you look closely, you can see a grid pattern, and this is caused by the diffraction pattern of the 5 dots that are being focused through the optical system. Okay, so right here is the diffraction pattern. I don't know if you can see it, but we found this really interesting. After we insert a lens in front of the microscope, we get the 5 dots back because it's taking the inverse Fourier transform of the image and it returns it to its initial state.
These are the results that we obtained from our measurements. As we can see, we got a quadratic result for coma, which is what we expected, and a linear pattern for astigmatism. And if you add these two together, a quadratic added to a linear function, we should obtain something like this. These are the values that we measured. We measured 2.8 times the tangential for a sagittal coma, and theoretically it should be 3 times the tangential. So the results were relatively close.